And welcome to Climate Chat. I'm your host, Dan Miller. And today we are going to talk about SRM, which stands for Solar Radiation Management, or sometimes Solar Radiation Modification, also known as Sunlight Reflection Methods. All those have the acronym SRM. And it's also known as solar geoengineering. It's things we do to reflect a little bit of sunlight away from the Earth in order to cool it to offset the impacts of climate change. And so, one of the big questions, we do know that it will cool the Earth and therefore sort of alleviate some of the impacts of warming. But the other big question is, will it prevent tipping points? And tipping points are things, well, we're actually going to get into a lot of what the tipping points are. So let's hold that off for just a bit. But tipping points are things that happen, and once they happen, you can't undo them, perhaps. We're going to look at that. And so that's a really big question. And there was a paper on that. And so we're going to go into that paper and look at what its results were, and going to do it in kind of a presentation, kind of compact format. So actually, let's get going here. This is the presentation. Can SRM prevent tipping points? And this all works. Okay, so the first thing is to remind you to like and subscribe, because we're trying to share climate information with everyone so everyone gets more educated and therefore understands the need for urgent action on climate, which is certainly not happening right now. Anyway, you can really help the channel by doing that, so we appreciate that. And this is the kind of front page of that paper. It's called The Interaction of Solar Radiation Modification with Earth System Tipping Elements. And so what we call tipping points, they call tipping elements. And Gideon Futterman is the lead author from University of Oxford. There's folks from King's College London, University College London, Tsinghua Shenzhen International Graduate School in China, and the Department of Forestry and Natural Resources in West Lafayette, Indiana, in the United States, and also Utrecht in the Netherlands. So international group of scientists working on this paper. But what I want to do is just start and give you the highlights, the main points, so you know what we're going to talk about, and then we'll get into more of the details. But kind of if you see nothing else, you can walk away with these main points. And so SRM, again, SRM meaning things like putting sulfur particles in the stratosphere, which is the main way, I think the one that they're assuming in this particular paper, but there's other ways to cool the Earth. But SRM, or solar geoengineering, may be able to reverse or prevent some, but not all, tipping points. And one really important aspect of the study is it says that this information is highly uncertain, which means that further research is needed on both SRM and the tipping elements and the impact of SRM on the tipping elements. So they're doing kind of a survey of the literature, looking at other studies, but they're pointing out that there's really not enough information given how important all of this is. And that's what that third point is. So more research needed on SRM, tipping points, and the interaction of the two. And they said, while SRM can help, it's not a get out of jail free card. They didn't use that term. That's the term I'm using. We like to think, well, we really screwed up here by not addressing climate change, but at least we can do SRM, and it's relatively easy compared to other things, and certainly easy compared to not doing it, because then you have to suffer the impacts. But while it does alleviate some of the impacts, it doesn't alleviate all the impacts, and therefore the smart thing to do is to actually reduce emissions and take CO2 out of the atmosphere. But so you just can't feel comfort that, oh, we have SRM and everything will be fine. As I do point out that SRM does help with warming impacts, and that's not really covered in this paper. It's really, they're talking about the tipping points, not just sort of the impacts that come just from warming. Although tipping points do come from warming too, but more to just the direct impacts of the warming itself, SRM can help with that. And the bottom line is, while SRM can help, we need to accelerate climate action in all aspects. So those are the main points. And before we dive into the paper itself, just a very high level discussion of tipping points themselves. What tipping points are is that a good way to think of tipping points is literally if you're sitting on a chair and you lean backwards a little bit, and then you sort of you push off with your feet, you lean back a little bit, then you let go with your feet, the chair will come back down to where it was. You can do that again, and you'll go back a little bit, come back where you are. But there is a point where you push too far, and instead of going back to where you were, you're in a totally different state where you're lying on your back on the floor. And that's a literal tipping point, and the climate works the same way. You can push it and it comes back. You can push it, it comes back, but there's a certain point where you push it and it doesn't come back. Now, there's a whole lot of tipping points. In fact, this paper covers 15 different tipping points, and they're different kinds. So you can't just make one statement that, oh, well, the tipping point is due to this and therefore that. But we are approaching tipping points. We may have passed some. And the interesting thing about tipping points is you very often don't know that you cross them until you have actually crossed them. And here is, let's see if we can blow this up a bit. Let's see. Yeah. So here's a list of tipping points and estimated temperatures where they might be triggered. Greenland ice sheet collapse could be triggered anywhere from like 0.4 C of warming up to about 3 C of warming. And I think this dashed red line is 1.5. It is 1.5, and we're already at 1.5 right now, and going rapidly towards 2, probably in the 2030s, which would be the end of this blue line. So you can see by the 2030s, we're going to be, and the red dot is sort of the estimated, the best guess, I guess, would be for what temperature is triggered at. Again, the red bar is the range of the minimum and maximum, and the dot is the central estimate. So here are the following tipping points that are triggered by 2 degrees. Greenland ice sheet collapse, West Antarctic ice sheet collapse, tropical coral reef die-off, northern permafrost abrupt thaw, Barents Sea ice loss, Labrador Sea current collapse, and mountain glacier loss. And, all of those are in some form of happening now. But in terms of tipping points is where you tilt the chair too far and now you're in a new state. In other words, they become self-reinforcing. Maybe just for example, with sea ice, when you melt some of the sea ice, now you have dark water exposed to the sun instead of reflective ice. So that heats up the water even more, makes it warmer, makes less ice. And so you get to a point where it's just self-fulfilling, and it's very, very difficult to change it, if not impossible, over human timeframes. So that's what the tipping points are. And the other ones that are theoretically triggered at later temperatures, West African monsoon shift, East Antarctica glacier collapse, Amazon rainforest dieback, northern permafrost collapse, Atlantic current collapse, that's AMOC, northern forest dieback, south and north, Arctic winter sea ice collapse, and East Antarctica ice sheet collapse. Now, this paper that published this graph is not the same as the one we're covering. So they use, I think, slightly different set, but most of these are the same, but a slightly different set of tipping points. Let's see, get back to here. And this is from the paper itself. And so in terms of tipping point, we're in this state over here. Let me do it this way here. So we're in this spot over here, and the drivers, the warming, the greenhouse gases that warm the atmosphere are tipping, they call tipping drivers, the things that are pushing the system to tip. And so in this case, the warming pushes us up the hill. The tipping point is the top of the hill, where if you go warm anymore, you end up in a new state. might be an ice freeze state. It might be an Amazon gone and just a scrub brush instead of trees, things like that. But they're saying that SRM can impact the tipping element or the state three ways. One, it can stop the external driver, like if it's warming that's causing the shift up the hill, then SRM cools the earth, so it would stop that warming, and then it could settle back into the original state. It could already be past the tipping point, but before the state settles into the new state, you could kind of claw back that warming and send it back. And then the third possibility is it's in the new state, and then SRM actually just gets it back over the hill and back to the other state. So those are the three ways that SRM could impact the tipping elements. Now, this is a table, like table 1 from the paper. Oh, by the way, the paper itself is linked in the video description, so you could read along if you want. There's a lot of information. It really looks at each tipping element in detail. And what we're going to do today is just like skim the highlights of it. In fact, there's 15 elements. I think we're going to cover like 8 elements or 7 or something like that in a little more detail, and then just list what the other ones are. And then talk about sort of the overall effect of what the study concludes. But this is how it's set up. On the left is the tipping element itself, and the top one is Greenland ice sheet collapse. We'll talk about that one first. The effect of the drivers, the things that are pushing the system towards a tipping point. Then the third column talks about reversibility. How once it's already tipped, how likely is SRM to bring it back? And then the last column is the strength of the evidence base, like how much research has been done on the tipping point and SRM's impact on the tipping point. And they're basically nothing's strong. It's either intermediate or weak or very weak. So there are no strong evidence for any of this. So we'll talk a little bit about that too. So that's what it looks like in the paper. But what I've done is put it into sort of the simple form that's easy to see. I use check marks. So they have sort of partially effective, and overcompensation, and maybe it does more than was before. And so that's 1, 2, and 3. And then they often are in the form of partial to effective. So if it's effective, it has 3. If it's partial effective, it's 2. And if it's just partial, then it's 1. So that gives you the number there. And then and the drivers are different for different tipping elements or tipping points. And then they give an overall assessment of how effective SRM will be. And then the number of question marks, it's not questioning that. It's just like how certain they are. It's 1, 2, or 3 question marks. So 3 question marks means, yeah, we're guessing. It's highly uncertain. 1 question mark, yeah, it's uncertain, but we feel a little more confident about the result. So that's the top part. And then the middle part is reversibility. The system's already tipped. How likely is SRM to bring it back from the tipping point? And in this case, unlikely. So put an X there, and you'll see different ones on tipping elements. And then how strong is the evidence of all of this? In this case, intermediate, which is the best case in this paper, is intermediate. So there's been a decent amount of research done on Greenland and on SRM's impact on Greenland and that kind of thing. In this case, I also added some notes that the interesting thing about so you think, okay, Greenland, the world is warming, so it melts. So, hey, if we make it cooler, then it will grow again. But that's not the way it works, because the temperature gets colder as you go up. The top of a mountain is colder than the bottom of a mountain. And in Greenland, the ice is very high, a couple miles or something. And when you melt the top, it also gets lower, right? The top of Greenland gets lower, whereas it's not a mountain, it's a mountain of ice. And then as you go lower, the temperature generally gets warmer. So so as you get lower, it warms up, and therefore it's harder to go back up again, even if you make it as cool as it originally was, right? If you make it as cool as it originally was, then the top of the mountain is very, very cold, but now the mountain's lower. So if you bring the global temperature back to where it was, Greenland's going to be warmer than it was because it's now the top surface will be warmer because it's lower. And so that's a feedback effect that once you get it past a certain point, it just warms on its own is a way to think about it. And another thing that's happening, which is sort of separate, it's part of man-made pollution, but it's not directly greenhouse gas, and that is black carbon. So black carbon is like soot, soot from coal plants or ships or these kinds of things. And when black carbon is deposited on the ice or even dust, it makes the ice less reflective, makes it darker, and therefore the sun absorbs it more and melts it more. So those kind of effects are happening in Greenland and also the Arctic sea ice as well. So anyway, that's the first one they covered. Basically, a very good chance that SRM will offset atmospheric warming. Will also have a positive, but again, less certain effect on precipitation. And these are like the main drivers. There could be other drivers too. I mentioned black carbon and surface elevation, of course. But the overall effect for SRM offsetting those drivers, it's partial effective, and with 2 question marks. So moderate amount of uncertainty there. Reversibility unlikely mentioned, and evidence intermediate. So that's Greenland. Let's go to the next one. Antarctic ice sheet collapse. Okay, now we're going to go to the other side of the Earth. It also, for atmospheric warming, yes, it does offset, but you'll notice only one check mark here because atmospheric warming is not the primary driver of Antarctic ice sheet loss. It's actually the warm ocean water coming up underneath and melting the ice. That's the second one, ocean warming, and that is not determined to be not at least in the short run, that SRM will help that. Precipitation, like before, would help. Then there's other major issues like circumpolar deep water-driven melt, the circulation around Antarctica, and it won't help. SRM won't help that, as far as they know. And all of this has the strongest amount of uncertainty because there hasn't been enough study of all of this. And reversibility, once you lose the Antarctic ice sheet, you're unlikely to get it back by using SRM. And the evidence for all of this is weak. So again, uncertainty upon uncertainty here, but they're trying to give their best estimate based on the research that's been done so far. Mountain glacier loss. So we talked about Greenland. The major glaciers are obviously Antarctica, ice sheets, Antarctica and Greenland. And there's also a lot of glaciers in the mountains, and we're losing them rapidly. And the question is, would SRM help? Would it reduce atmospheric warming? Would the main driver being atmospheric warming? It would help that for sure. It would help with precipitation. It would, and overall, it's estimated to be partial to effective in reversing the drivers of mountain glacier loss. But then the question is, once you have lost the glaciers, what's the probability that SRM can get you back and reform mountain glaciers? And there they estimate that it's likely partial effective. And the evidence for this is intermediate, so better than some of the others. Whoop, I think I did 2 there, so let's go back. Winter Arctic sea ice abrupt loss. So we have sea ice in the Arctic, and in the summer it's getting lower and lower, but actually the amount of sea ice in the winter is also dropping, and you can get into a stage where you lose it not only in the summer but in the winter too. And so this is talking about the winter. Atmospheric warming would help. I believe that's partial, and the overall is, and then that's the main driver. And overall, it would they estimate would be partially effective at reducing those drivers with 2 question marks, a moderate amount of uncertainty. And the interesting thing, reversibility, they say likely effective. Actually, I only put 1 check mark for reversibility, but because it's effective, that would get 3 in the driver section. So that's a positive thing, and evidence for that's intermediate. Then we go to the summer sea ice decline at both poles, the Arctic and Antarctica. Atmospheric warming would be reduced, so that's a positive. Ocean and atmospheric circulation, which affect those, it's unknown, so they don't even put anything. Overall, they think it could be partially effective with 1 question mark. And reversibility, they say it's actually likely. Oh, here I did put two check marks there for that. I'm not consistent on that one. And evidence is intermediate. Boreal, oh man, I'm going 2 at a time here. Okay, boreal permafrost thaw. So, around the Arctic, we have permafrost, which is supposed to be permanently frozen ground. It's like ancient frozen ground with lots of biomaterial, dead plants and things like that. When that melts, it turns either to CO2 or to methane. There's actually, in the permafrost in the northern hemisphere, there's about twice as much CO2 as the entire atmosphere holds. So obviously, if the permafrost thaws, that's a really big impact, especially if it thaws in puddles of water, because when it melts in water, it creates methane instead of CO2, and methane's 120 times as powerful as CO2 while it's in the atmosphere. The good news is it doesn't last in the atmosphere a long time like CO2 does, like 15 years or so, where CO2 lasts for hundreds to thousands of years. But anyway, back to permafrost thaw. Main driver is soil warming, and it would help address that. Also, precipitation. I guess when it rains, I think it helps melt it faster, and cooling the earth would maybe stop that. Impact of wildfires, because if you do SRM, does that make more wildfires, make less wildfires? They don't know. Same thing with vegetation. They don't know. And so the overall, they give that would be partially effective. I wonder why I gave it 3 there. Okay, with double question marks. Let's go look at that again. We're at boreal. Okay. Oh no, it said I said it wrong there. So it says it's actually overall effective. So I had partial here, but it should say effective. That's why I got 3 check marks. I forgot to change partial to effective. And then reversibility, once it goes, it's unlikely to fix that. Although I don't know, that one I'd like to look into more, because you would think that if it got very cold up there again, it would refreeze the permafrost. Even though whatever you lost, it doesn't help you there, but it would stop it from going further. Evidence is intermediate. Okay, this is, it keeps going twice. Marine methane hydrate loss at the continental shelf. Let's talk a little bit about this one. This is sort of one of the game over kind of things. There's something called hydrates, or sometimes called clathrates. And you can think of it as methane trapped in an ice shell. You can think of it like a snowball of methane, different ways of thinking about it. And it exists usually deep in the ocean at high pressure and cold temperatures. And there's a lot of this. There's, I think, as much methane hydrate existing in the oceans and the Arctic Sea and things, as much of that as all fossil fuels combined. And we don't go after it because it's unstable if you do it. And the point is, if global warming gets so strong that it starts warming at these lower elevations in the ocean around where the clathrates exist, and it starts melting them, then they're going to release their methane, which initially gets absorbed by the ocean on the way up and doesn't enter the atmosphere. But if you get enough of it, it will bubble up into to the top of the ocean and go out into the atmosphere. And that methane would be very powerful warming, so it could just really screw things up, I guess is a good way to put it. And so in this case, they looked at that as a tipping point because, basically the ocean warming so much that it releases all this methane, which warms the Earth even more, which releases more methane. So what the big driver is ocean warming at the depth of the shelf where the clathrates exist, and the answer is unknown. We don't know if SRM is going to help that or not. Remember that SRM is cooling the atmosphere, and it does end up cooling the oceans too eventually, but whether it's going to do this in time is unknown, and therefore the overall is unknown. And in terms of reversibility, they say that's not applicable here because it's a threshold free feedback. You basically warm, you get more release. You warm more, you get more release. But if you cool off, then you should get less release. The evidence for all this is weak. And so my point here is this is all super highly uncertain, right? So they say, well, we don't know. We don't know that that's a threat. So we can sit back and relax because there's really no definitive information that this is a serious threat. Well, I think I use the quote, uncertainty is not your friend. Just because, you don't know for certain how bad it is, it's not something you should feel comfortable about. You should actually be just as worried. And from a risk management point of view, you should assume the worst and hope for the best. So that's methane clathrates. Probably should do a whole show on that, actually. AMOC collapse. We talk a lot about AMOC collapse. This is the Atlantic meridional overturning circulation, the major Atlantic current that brings warm water from the tropics up to northern Europe and brings cooler water back down. And a lot of signs that it's weakening, and more research in the last couple of years. And we've done a lot of shows on this, showing that it might collapse starting at reaching its tipping point. That doesn't mean it stops at that time, but maybe around 2050, it's gone past the point of no return. And then the question is, can SRM help reduce the drivers of AMOC collapse? And in this case, it's quite positive in terms of surface ocean warming. It's partial to effective, precipitation evaporation effective, Greenland ice loss, partial to effective, sea ice loss effective, and therefore the overall result was partial to overcompensation, which there's very few overcompensations in this paper, and therefore getting 3 check marks, but with 2 question marks, which means a reasonable amount of uncertainty on all of this. And then in terms of reversibility, they said uncertain, but possibly partially effective. So that would mean, maybe it can help restore the AMOC, especially if it's maybe tipped, and if we did nothing else, it was on its way to collapse, but maybe claw it back before it gets all the way collapsed. And the evidence for this is intermediate. There's actually been a reasonable amount of study on this. In fact, we did a whole show on how SRM can help stop AMOC collapse with Peter Irvine, I believe, who's actually, I think, one of the co-authors here. So check out that show if you're interested in that. And so I'm not going to go through all the tipping points that this list, because you can read the paper and the paper is linked. But here are the other tipping points covered in the paper: subpolar gyre collapse, Antarctic bottom water collapse, marine stratocumulus collapse, Amazon rainforest dieback, shallow sea tropical coral reef loss, Himalaya to Sundarbans system biodiversity loss. That's from the Himalayas down into the India, Bangladesh, Pakistan region, a northern boreal forest dieback. So besides the table, there's also a sort of like a chapter or a section on each one of these, and it describes what it is and what the drivers are and things like that. There's a lot of information in this paper. I think it's 40 pages long or something. But however, if you're interested, especially if you're interested in any particular tipping element here, you can go and read about that one. You don't have to read the whole paper. So that's good. Now, in terms of the overall impacts, so now they did 15 tipping elements, they call them. We'll call them TE here. Of all of those, SRM will probably reduce tipping drivers, the things that push the tipping point over the edge, reduced tipping drivers at least partially for 9 of the 15 tipping elements. And it did not worsen tipping drivers overall for any of them. So in other words, SRM didn't make it worse. Even if it didn't help, it didn't make it worse for any of them. Although in individual cases, I'm talking about overall, there might be some cases like maybe SRM hurts certain regions of the Amazon or something like that. So regionally or a sub element could be impacted negatively. But for the most part, it helped in 9 of 15, didn't make any worse overall. They didn't have any judgment on the impact of SRM on 4 tipping elements due to lack of evidence. They just didn't have enough to go on even to make a guess. Uncertainty was judged to be considerable to very large for 13 of the 15 tipping elements. That really tells you that a lot more work is needed, a lot more research is needed. And the evidence base was judged as weak or very weak for 8 tipping elements and intermediate for the remaining 7. So it wasn't strong for any of them. And continuing with our overall results, compared to SRM's effect on drivers, its potential to reverse ongoing tipping is much harder to assess. In other words, there's reasonable, amount of research on how cooling can, reduce a driver of the tipping. But once the tipping has already occurred, there's much less research available to judge what happens then. But they did say a well-implemented peak shaving SAI stratospheric aerosol injection, that's putting sulfur particles into the stratosphere. It's a form of SRM. A peak shaving SAI program may reduce the probability of tipping for most tipping elements or tipping points. And using SRM to reverse tipping once it started may be much more difficult and uncertain. So another way of saying it, better to start early. I mean, some people think, well, we're going to try to reduce our emissions, and if that doesn't work, then we can use SRM. That might not be the right strategy, because if you do that, you've basically given a chance for all these tipping points to be passed. And then once you do that, you're kind of screwed. So best to start early. But certainly this paper, if it says nothing else, it says we need to rapidly increase research into all of this, into SRM, into the tipping points, and into the interaction of SRM and the tipping points. And that's super cheap in the overall scheme of things. We're talking about, millions and millions of dollars, or maybe $1 billion altogether, but that would be, but not enough is happening now in that regard. And I made this point before, it's not a get out of jail free card, SRM. SRM will be very helpful as people, we've done many programs on this, but basically the objections to SRM is that there might be side effects. Certainly will be. That's not the question. The question is, will the side effects of SRM be less harmful than the side effects of not doing SRM? And I think this paper is one more indication that the side effects of not doing SRM are really unacceptable, catastrophic, perhaps civilization ending, whereas the side effects of doing it are probably more manageable than the side effects of not doing it. There's other objections. There's the moral hazard argument, which says if you do SRM, that will stop people from reducing emissions. Well, I just say, well, then you're just saying that we're not going to take climate action seriously. And if we're not going to take climate actions, if we're going to continue to choose to fail, then we will. But if we choose to succeed, then we probably include emissions elimination, carbon dioxide removal, and solar radiation management as part of the success plan. Let's see. And that kind of sums up this summary of this paper. Remember to like and subscribe. And we are going to go to here. And let's bring in Leon here. Leon, hi. Good to see you.
Hi there. Likewise.
Hi.
Hi, Dan.
Your thoughts on this, the little summary, at least, of this paper, or questions?
Yeah, I think it's always good to focus on the different tipping points, right? Indeed, the conversation we had on the AMOC, I think that really shows that if we want to do something to save in many ways European agriculture, like I think that's the only way we can keep the AMOC from shutting down. It is sunlight reflection methods, especially over the northern hemisphere, and especially also as some research shows over the certain regions of the if you do, for example, with marine cloud brightening, so brighten the oceans over regions where these low clouds, there's generally more of these low clouds, so it's also possible to increase the cloud cover in these regions and then increase the amount of sunlight reflected to space, and then have, in a way, what that would do is keep the heat from the southern hemisphere and from the tropics flowing northward, keep that stronger than it would be without that regional cooling.
I think, by the way, you're making a good point, because AMOC collapse, I call it sort of the mother of all tipping points. It kind of screws up everything. I mean, yeah, it makes Europe really cold and screws up the arable land in the northern part of Europe really badly. I think the one study I saw for a particular country said that England loses 70% of its arable land if the AMOC collapses. But it screws up everything. It lowers rainfall across the entire northern hemisphere, not just Europe, and that obviously impacts agriculture everywhere. And since most of the land is in the northern hemisphere, then the southern hemisphere, that's a really big deal. And plus, changing the storm patterns, and basically whatever we did to set up civilization to have the right kind of agriculture in the right kind of place, it changes it all up. It just turns it upside down. And
Yeah,
because all of these,
civilization developed in the current climate, right? And
right.
Of course, we can adapt to changes, and we are quite good at adapting as a species, especially now with technology. But it will be really hard to adapt to rapidly, and that rapidly means even not just from a geological perspective, but even from a human perspective. Within 5 years, the European climate changed when the AMOC collapsed thousands of years ago, and we can see that in these small corals and depositions on these in these volcanic lakes in Germany, where the entire climate of Western Europe changed in an instant,
right,
within 5 years. And indeed that's from a European perspective, but the rainforest, for example, the Amazon rainforest would also be highly impacted.
Yeah.
On top of the the impact of warming and the impact of deforestation, and so it all these threats, they add onto each other, and then the tipping point of the AMOC could cause and contribute to the tipping point of the Amazon rainforest, and then indeed also impact the West Antarctic ice sheet, and so it's that's to me the most important reason why I would encourage very rapid research on a really global level, and billions of investments to make sure that we really understand better what can be done, what the risks are, what the associated risks are, what can we reduce those risks? Mm-hmm. Are the remaining risks acceptable for sunlight reflection methods?
Yeah. And by the way, you said about the AMOC collapse would impact the Amazon. So this is part of the craziness of this whole subject, because people say we shouldn't do SRM because it might possibly impact the Amazon in a negative way. Well, if you don't do SRM and therefore the AMOC collapses, then you really screw up the Amazon. So, there's nothing's really clear cut. You're trading off risks. Like there's nothing you can do at this point, whether we could have 50 years ago, but we chose not to do anything. But there's nothing we can do now that ends up with everything being okay. There's going to be problems no matter what we do, but some are like really big problems, like AMOC collapse and other things, and others are still really big problems. I don't want to say any of these aren't big problems, but maybe manageable, from a civilization point of view. But we have to
be
work
able to
quickly,
manage
though.
it, right?
Say again.
That's all. The goal is to manage the risks. That's all. That's the goal. At least first to do the research, and then the goal is researching how we can reduce risks. And that's often, of course, it's not a black and white debate, but some, of course, in the media, let alone social media, it's often portrayed like that, like you're either for it or against it. And it's with many subjects, like whether it's nuclear or windmills or genetically modified organisms or SRMs, right? It's often like either for or against. Well, the world doesn't work like that, right? It's not black and white. Everyone wants to reduce risks, especially if they are existential. I don't think there's any.
I'm not sure that's true, by the way. We're certainly not doing that. we know these are existential risks. We've known it for a long time.
If you
We're
ask
not doing
people,
anything, so I'm not sure it's true that maybe we
if you
want
ask,
to, but it's wanting to and doing it are two different things.
That's for sure. I'm not arguing with that. I'm not, like, if you ask people, most people, I think, the vast majority, negligible small amount of people wouldn't want to reduce existential risks, right? But indeed, like, we're not doing that, and it's of course easy to say yes to certain questions, like, do you want world peace? Do you want to reduce existential risk? But then what's next? And then it's much more difficult, of course. It's these are very hard to difficult subjects even to talk about, and even amongst people who have the same goals and the same who are rational. There's opposing approaches, and you should say this or no, you shouldn't say this, or many people can misinterpret what you're saying. Like, if I'm doing research on aerosols, people think I'm campaigning for increasing aerosol emissions, while I'm just trying to understand the biggest uncertainty within climate science, right? And that's just a very small example of in a way, not even innocent, but like should be beneficial, right? To try to reduce the biggest uncertainty in climate science, but often many interpret it like I'm doing something evil just by doing crucial research, right? And let alone when you start really to talk about SRM, then it's you get a lot of pushback, of course, not on the merits or on what you're saying, but because you make people feel uncomfortable.
Okay, let's go to Stacy, get her question, and then Eli, and then we'll go to some audience questions. Let's see. Hey, welcome, Stacy. Let's see if we got any cats in the picture there. Wait.
One sleeping, one back there, and Rocky he's lounging on the ground. Well, he'll get desperate at some point. So,
like this video because of the cats, people.
Yeah, like the video because of the cats. Okay.
We're here to please. If only the climate were doing the same. I don't have a question there, and there are so many good audience questions. My only thing is I will read a comment that somebody, I totally agree. Jacob said, prediction: we will attempt SRM before we see decreased fossil fuel in fossil fuel use. Yes, I agree, and none of us want that. I cannot stress enough.
Mm,
None of us want this to happen, but we all would like to live, and so in a habitable planet like we have enjoyed. So again,
I'm
this
not
we
sure
are
that's
not
technically true. So
what's that?
technically, what we're talking about is annual fossil fuel emissions and CO2e, right? It's
Yes.
kind of leveled. It's still growing, but at a slow rate. And if China truly is reducing, and they're the biggest contributor right now, if China truly is reducing their emissions, which is predicted to happen like this year or last year, we'll see. And then again, even if you see it, you're not 100% sure of the data. But let's just say that happens, then it is possible that the world will. This is not rapid decrease in fossil fuel emission. I'm just saying, less the next year than it was the year before. Still currently at a record high. So not a good thing, but at least the right direction. That could happen certainly in the next 10 years. And I see SRM starting as soon as 10 years, but probably not a lot sooner than that. But so anyway, I'm not sure that's technically true, but it's
What
not really that big a
so
deal.
what were you answering that you think I was saying that's not because
That fossil fuel, we will see SRM before we see fossil fuels decrease.
okay. I guess I would modify that slightly and say emissions.
No, I'm talking about
y-
emission. I'm sorry, emissions. Yeah,
But
right, but
emissions
significantly, right?
decrease.
You got
more people, more meat, less carbon sinks because we're chopping down the forests and things like that. We are consuming the electricity for all of our computation, AI, etc. It's like we are increasing. I don't see us
can I say what I
decreasing.
agree with?
Okay.
Okay.
I can imagine, and again the disclaimer is not what we want to happen, but what based on the past experiences, what will likely happen is that SRM will be implemented, hopefully with good scientific backing and reducing risk, before we see the rate of atmospheric CO2 decrease. And that's because indeed
Wait. The rate of
the rate
CO2
of atmospheric
increase,
CO2,
isn't
the
the
rate
rate already decreasing right now? The rate
no
of
the
increase
rate
decreasing?
even the emissions, the what you said, okay, the emissions are more or less stabilizing. I can agree with that. And
Okay.
why it is, I wouldn't applaud the Paris Agreement
No.
for COVID and for energy wars, but you're right. The CO2 emissions more or less stabilized, still increasing, but more or less stabilized relative to the rate of increase before.
Yeah.
But the rate of atmospheric concentration increase
Oh, okay. Yeah. That's which is
kept
different.
increasing.
Right. Because we have natural sources. The Earth warming naturally
And we have
gives off
natural
more
sinks.
CO2. And you're right. The
We have
ppm
net
per
sinks.
year is going up at a crazy rate. Yeah,
No, we have net sinks. So
and the sinks are dropping. Yeah. That's true.
naturally, without our emissions, CO2 in the atmosphere is decreasing, right? Because the oceans take up CO2 because the atmospheric concentration is so high, and the plants grow faster because the atmospheric concentration of CO2 is so high. So the planet Earth is decreasing the atmospheric concentration of CO2 by taking up CO2 in the biosphere and in the oceans. But that especially the rate of the biosphere, the uptake by the biosphere is decreasing.
Right.
And it was very low the past years. Also due to El Nino and more forest burning in Canada and in Russia, for example. And that caused the rate of atmospheric global average CO2 concentration in the atmosphere to increase at a record amount, even like shattering the previous amount by, I don't fully remember, but I think about 0.5 parts per million or something. It will
so that's actually quite interesting, and it might be worth a show, actually. Because everyone, there's a certain group of people, climate people, who say our number one thing has to be reducing human emissions. Do that before you do anything else. Don't do carbon dioxide removal. Don't do SRM. Just do that. And it is true that, as we were just talking about, we might actually start reducing human emissions. That does not mean that the increase in CO2 in the atmosphere, which is the real thing that matters, that might not level off. That might continue increasing because we're still pumping obviously lots of greenhouse gases, and the sinks are decreasing, and and this is the part which I haven't actually seen a lot of good data on, or maybe you measure it as the sinks decreasing, but the Earth itself is giving off more CO2 as it warms. There was a paper long ago that said going to 2C of warming would make the soils release something like 300 billion tons of CO2, just from the soils giving off more CO2.
Aerobic combustion.
Increased microbial activity in the soils. That one thing. And so this is all
and if there's less oxygen available, but also if there's less sulfur available, there will be more methane produced rather than CO2, which of course is also a strong greenhouse.
Yeah. Okay, so anyway, let's bring Eli in with his question, and then let's get to the audience questions. And Eli, welcome. Eli, you there?
Hi, thanks. I'd like to emphasize. Can you hear me okay now?
Yes, great.
Can you?
Yes.
Okay. So I'd like to emphasize something from that graph that you had from the other paper about the tipping elements. Though the gray bars, the ranges, it's been a while since I read that paper, but usually in scientific papers, like the default range is one standard deviation, but sometimes they will make it the 90% certainty range, right? But for some of these feedbacks, like especially the methane clathr rates, if even we're passing that 10% chance, right? That is just so dangerous because, and again, there are many scenarios with methane clathr rates. It can be gradual, it can be abrupt, it can be gradual, and it can trigger marine slides, and then it becomes abrupt, and we will not see that coming, right? So very, very huge risks. So even if huge consequences. So even if the risks are relatively slow, we just know so little about the distribution of these things and how they're actually going to respond that, like you said earlier, Dan, uncertainty is not our friend. Mm-hmm. And the only appropriate thing to do is to be very cautious and to be very, very prepared to do even more than you hope.
Risk averse.
I think we just lost you there. Okay. But it's like if you're willing to do that, you should be willing to play Russian roulette, and I don't recommend doing that. But even though your probability of getting your head blown off is only 1/6, still not recommended because the outcome, if it happens, is pretty bad. So that's the same as the situation we're in. Okay, so thanks, Eli. And then Stacy, what questions do you recommend?
Okay, can you do a quick refresher of the comparison between mining for renewables and fossil fuel extraction for me?
Well, it's kind of a different show, but you can do a very quick one.
You have that percentage that it's like.
Well, it's 500 to 1. So mining of fossil fuels is 500 times more than mining for the increased amount of minerals and metals and things that we need to have 100% renewables. So switching to 100% renewables would reduce all extraction, not just not just mining for those materials, but if you include fossil fuels in that, then it would reduce all mining by over 99%. And the one way to think about it is one ship full of solar panels replaces 100 ships full of fossil fuels. Because that ship full of solar panels, Bill McKibben was on the show and he used that as an example. It's not just today's energy, it's for the next 30 years you get energy from that ship. Whereas all those other ships, it's one-time use, burn it and got to go again. And so, yeah, there's a lot of information on that, but that's not so much today's show. But anyway,
no, there was some chatter about it, and I couldn't
quick
remember.
answer
Now
there.
maybe I'll have it committed to memory. So there was some when we talk about solar radiation management, we hear things about chemtrails.
Okay.
Can you explain the difference
Okay,
here?
so chemtrails is a fake conspiracy theory that says the government, for a long time now, I don't know, decades, have been secretly putting chemicals into airplane fuel to control the population. I don't even know. It doesn't really matter whatever the purpose is, but it's a conspiracy. And the people think this is true because they look up in the sky and sometimes they see airplanes with a trail of white cloud coming out the back, and they say, "Well, there's the proof. Look at this." And that's just condensation. That it's hot exhaust coming out of the airplane, and when the atmospheric conditions are correct, that condenses into a cloud, and you see it. But so this has been going on. This conspiracy has gone on for a long time. But remember, if this is true, there has to be thousands and thousands of people who are keeping this a secret. I mean, every fuel loader, the people mixing it somewhere secretly at the airport. I mean, there has to be happening all the time. And every one of them has to keep it a secret. And one of my favorite quotes of all time is Benjamin Franklin, who said, 3 people can keep a secret if 2 of them are dead. And so now take thousands, I mean, that'd be tens of thousands, hundreds of thousands of people are keeping this a secret. Okay, that's chemtrails, which is a fake conspiracy theory. Sulfur aerosol injection would sort of be that. It would be taking an airplane, flying it very high, by the way, up into the stratosphere, and releasing sulfur particles. By the way, airplanes reduce some sulfur particles today. Ships do, coal plants do. Anytime you burn a fossil fuel, you get sulfur because there's sulfur in the fossil fuels. But this would be doing on purpose, sort of at a massive scale, and it would, in some sense, look like what the fake chemtrail thing is all about, but it would be real. So anyway, that's the difference. It's thought to been happening for decades. It hasn't. One might happen starting in a decade. And it would be real, but anyway, I hope that clarifies it.
Yes.
I have a nice anecdote about these chemtrails. When a friend of mine, he did his PhD on clouds, and he was always looking at these lidars and radars and looking at this data. And when I visited him in Delft at the Technical University where he was working, someone was also, who wasn't, of course, an atmospheric scientist, talking about these chemtrails, and then he was like, okay, let's look at the data, and we could just look at the atmosphere because we had all these instruments there. You could see that plane flying there. You could see that it was going into this layer of the atmosphere, because the atmosphere is also layered. So the troposphere is layered, and you could see that it entered a region with a high amount of water vapor. Because you could see that from the instrument that there was more water vapor, and then you could see that once it entered that layer, then this chemtrail, or it's actually contrail, started to form, because you had these particles from this airplane, and this turbulence caused this cloud condensation. Aerosols, we call aerosols like sulfides, we call them cloud condensation nuclei, because that's where water in the atmosphere condensates again and forms these small droplets, water droplets, or ice crystals, which are clouds, right? If you have a lot of them, those started to form behind the airplane. And that was really nice that we could see, right, just from our window, combined with the data on the screen, we could see it all happen. And we all know this. If you study this, you know what happens up there more or less, right? Of course, you can just talk about all these microphysics and and look at in cloud chambers what happens, and there's a lot of uncertainty, but the basics are really well understood. So there's no conspiracy there.
All right, let's see. I want to go to this question here, so I'm going to jump ahead, Stacey, because I just saw this one, and it's a very long one. I'm going to summarize it. She said, Charisse, SRM researcher here, she's looking at changing the surface albedo, I think by making the long-term, it's a little hard to say what's going on here. Second life to decommission blades using wind composite, long-term real life marine environment. A high albedo white reflection on water helps cool the water. This is true. And someday we're going to do a program. There's another form. I'll say it here today. There's another form of SRM that never is talked about, but it was sort of the first one I ever heard about when I went to a solar geoengineering conference. I think it was one of the very first ones in Monterey, California, 15 years ago, maybe longer. And I met somebody who was working on microbubbles. So when you think about a wave crashing on like on the beach or something, you see it's white. That's because there's air bubbles in the water, and that makes it white, and that reflects the sun. And even on the surface, you fly over the ocean, you see white caps are called, right? White caps are waves crashing on the ocean. Well, what if you could make those bubbles yourself, which you can, by the way, just think of a jacuzzi tub, a hot tub, and you see it's all foamy on the top and it's white. So if you could make those bubbles last a long time, you could have ships going around the ocean simply making the ocean white wherever it's behind it and make it last long enough, which there are ways to do that, then it would be a way of cooling the ocean rather quickly and harmlessly. In fact, it turns out that it actually helps the marine life underneath when you do this, actually, and there's things like that. So that requires a whole subject. I'm trying to get this guy on to do a whole show on that, but it's a sort of this unknown or never talked about way of possibly doing SRM that requires a lot more study before it can be possible, but it's still an interesting one. Okay, what do you have there, Stacey?
Just that, well, first, Nadia wanted to say that some of the chemtrail conspiracists wrongly claim that chemtrails are already ongoing SRM efforts. And to that point, there was a question, what makes sulfur a better SRM material than the aluminum, barium, strontium, manganese, polymer fibers, micro and nanoplastics, and graphene they already use?
I'm not sure that they already use part, but the reason we focus on sulfur, I guess, are two major reasons. One, it is what volcanoes release, large volcanoes release. And so we have experimental data that says putting sulfur particles in the stratosphere of a certain amount does cool the planet because we actually observe it, like in Mount Pinatubo, 1991. So first one is, yes, we know it's available. And two, and we also therefore know it's not an environmental catastrophe, since it, I think Mount Pinatubo put 20 million tons. And by the way, we're putting 70 million tons in the atmosphere every single year today in the lower atmosphere, where it only lasts for 1 week. And that's cooling the atmosphere by 0.5 to 1 degree. And that's killing 8 million people a year by doing that, because that's down low is where we breathe. Up in the stratosphere, we don't breathe it. So we know a lot. And the second thing is we have a lot of sulfur. it's like really available. However, there are other companies. In fact, there's a private company, and it's kind of weird, a private company to do SRM, because it's not clear how you make money from it, but they think they will. And they're looking at some other particle. And there's a lot of people that have looked at what is the ideal particle for SRM. You want it not to react with the ozone layer. You want it to be harmless when it falls to Earth. You want it to be plentiful supply and inexpensive. You want it to have the right optical properties to reflect the sun. There's a lot of criteria, but since it happens naturally a few times a century with sulfur, we have a base of information on that one that gives it a heads up. That's or a leg up.
Let me talk a bit about the troposphere as well, about the lower atmosphere where the weather happens. Because there, of course, we have a lot of, indeed, as Dan mentioned, it was about 140 million tons, and now it's about 70 million tons, or maybe lower, we don't know exactly, of sulfur emissions. But the oceans, for example, algae, also produce sulfur. And that's about 20 million tons of sulfur dioxide, which is a gas. And that's also one of the reasons why I think if you look at, for example, aerosols, the easiest aerosols to make, which will most likely cause regional or global cooling, are in many ways sulfate aerosols, because when this sulfur is burned, or when these algae emit sulfur dioxide in the atmosphere, it's a gas. Many are confused sulfur dioxide. They say it's an aerosol, but it's not an aerosol, it's a gas. And then it forms sulfates, mainly sulfuric acid. And then because it's a gas, they form these very small microscopic particles, which because then you have many small particles and that creates all these small droplets and small ice crystals, which rain down much less fast, and also create bigger and whiter clouds, which reflect more sunlight. So that's also a reason. It's easier if you want, for example, to try to make sea salt. It's much more difficult to make these very small sea salt crystals. Salt aerosols also reflect sunlight and cause cloud formation, but it's more difficult to get the right particle size. So that's also not a reason to start emitting a lot of sulfur, but that is a reason why, and combined with what you already mentioned, that we know a lot about relatively a lot about what happens already in the real world, because we can learn from that with the inadvertent aerosol experiment, as we call it, from reducing the sulfur emission from shipping, being one of the lessons, the real world experiments, which in many ways is still ongoing. Of course, we are still learning from that. The more data comes in, where we can learn from what happens in the real world when based on what happened in the past.
Okay, so thanks. And so Stacy, what are a few other
Oh yes.
comments we can get into?
Let's see.
We pinned some as well.
In Suk Young asked, jet streams collapse are also tipping points, and ENSO, which is El Nino Southern Oscillation Amplification.
Well, yeah. So there's something the jet stream, which is this high altitude wind circling the Arctic. As the Arctic warms up faster than the rest of the world does, that decreases the temperature difference between the equator and the North Pole, and that makes the jet stream sort of lazier and wavier, and that's what gave the crazy winter conditions in the United States a week or so ago. So that is an impact of climate change. But if you could restore the coldness in the Arctic by using SRM, that should make it get stronger. So I wouldn't call it a tipping point. It's more of a direct effect of the warming and the change in the temperature differential between the North Pole and the equator. I forget what the second one was, but anyway, that's a quick answer for that. So
there were two related questions. Old Jack Wolf was asking about, did they look at the effect of decreased photosynthesis with plants in SRM, since sunlight will be decreased with SRM? And Im Suk Young asked about the extinction of phytoplankton Oh no, that has led to a missing carbon sink.
Because of
or
this.
can it? Yeah.
So the question, they have looked at that. I mean, more research is needed, but in general, it's only going to decrease direct sunlight by 1 or 2%. That's all you have to do to cool the Earth. But it sort of makes it a little hazier rather than direct sunlight, and that actually is usually good for plants. Sometimes, for example, farmers set up what's called shade houses, where they just put like a piece of canvas above the plants. I mean, for hectares and hectares, and that improves the growing, because the sun directly shining on the plants is not always the best thing. And so
more diffuse sunlight as
well. Diffuse sunlight helps plants grow. So that's the quick answer. It's not expected to be a major impact on agriculture. Might actually help agriculture. Okay.
Depending on
our predicament asked, I thought AMOC collapse was driven by fresh water from Greenland, and SRM won't help that?
No, well, actually it would. But that's the whole point. What is causing the fresh water from Greenland and the Arctic, by the way? So it's both of those. The Arctic is melting, the sea ice is melting, and when that melts, that's fresh water. And the Greenland ice melts, that's fresh water going into the North Atlantic, and that's what's impacting the AMOC. Obviously, if you cool the Greenland and the Arctic area, that would make it colder up there, and there would be less melting and therefore less fresh water. And so it's very direct. It would help directly relieve the main driver of AMOC collapse.
Yeah, and there's also indirect effects, and it's well, I think we've gone into the science there in the past, and if you really want to understand all these different interactions with different weather patterns and different cloud fields and more precipitation, because of course precipitation, rainfall is also fresh water, and where that rain falls also impacts the density of the water, and of course it's also temperature, ocean temperature also influences the density, because if the ocean is warmer, the molecules move faster and is less dense than if the ocean is cold.
Okay, another one. Natural emissions, like from permafrost, are emissions needed to... No, okay. I'm gonna have to stop and read that and make sure I have it right.
Here's one, by the way. I'll just throw in one here. This one is saying, hey, if you do SRM, that could hurt the ozone hole or make it worse, I guess. And that is true, that sulfur particles in the stratosphere do have an impact on ozone, but it's not, this guy said, will destroy the ozone, and that's not true. It would decrease it a little bit, equivalent to a year or two of recovery. So while, and we had scientists on talking about a study done that compared the increase in cancer deaths due to that effect versus just the increased death due to extra warming from if you don't do SRM, and it was like an extra 400,000 people a year would die if you don't do SRM, and that was only those two effects. It didn't go into all the other impacts that SRM addresses. So that one, I think, while it's a real issue and needs more study, it's not as simple as what this person is saying.
And another interesting thing I learned, and there's some science about it, and might be somewhat different. Some might have different thoughts about it, but that a big reason why the skin cancer rate increased in Australia, Tasmania, and New Zealand wasn't the decrease in the stratospheric ozone concentration, because that's more south, and the sun doesn't really shine much through that layer of the atmosphere. But it was much more because of decrease in air pollution. Because of course,
really?
air pollution
Australia?
also. Sorry.
In Australia, it was a decrease in air pollution that caused the increase in skin cancer.
Yeah, and we see the same. We see it also here now in the Netherlands, where we had more than an hour of additional sunshine, and so that's no clouds a day. So more than and
I
so
see.
our farmers. We have this. We live on a farm, and we get this farm magazine every week, and in this farm magazine, it said that the older farmers have higher chance of getting skin cancer because they are not used to using sunscreen as much. Because when they were farming in the 80s and 90s, there was much more air pollution and there was much less UV radiation, so they wouldn't get as much cancer, skin cancer, or sunburns, right? And so now we have to learn and adapt to these changes in getting much more solar radiation reach the surface here as well.
That's really interesting, by the way.
No matter the concentration of stratospheric ozone. And I'm not saying we shouldn't care about what the impact of aerosols is on the concentration of ozone in the stratosphere. We definitely need to do that. That's why we need to look at the risk, and if the risks are too high and the risks are much higher than the benefits of doing, of course we shouldn't do it. But it's not like, oh, big no, let's not do it because of this. No, it's not black and white. We have to do a rational assessment and consider all the pros and cons. And then if the risk is the AMOC shuts down, right, we might consider, and not we, but stakeholders, Europe as a whole, or might start to consider trying to keep the AMOC from flowing.
By the way, that's really interesting. You got to send me the link to that study because I want to send it to David Keith because he's the one who did the study saying, hey, let's just look at increased cancer rates from a weakened ozone hole versus the savings from people not being as hot, but I don't think because I looked at the study, I don't think they took into account what you're saying. So this was saying SRM would bring back clouds since warming decreases clouds. We now know that. That's a recent finding. We had George Salutis on who did the research on that. So we do SRM. It cools the earth. We get more clouds and it decreases cancer. Even though, even if it increases it a little bit from the change in the ozone. And by the way people work is, this is the trolley problem. They care far more about the thing we did than the thing we stopped from happening in a way. One is considered natural and the other is not, so they would actually care that there were 3 more people killed from the decrease in the ozone hole, even though 10,000 people were saved by the decrease in temperature and the fact that increased clouds and stopped less cancer. It's funny how that all works. And that's by the way, we did a show on this, but it's one reason people are so against SRM. It's not that, you might convince them that it actually saves millions of lives, maybe billions of lives. You can convince them of that maybe. But as long as it's responsible for thousands of deaths on its own, they'll feel but we did that. And those 1,000 deaths is worse than saving 1 billion lives. It sounds weird, but watch our show called The Trolley Problem and Climate Change. And you'll see all about that. Okay, let's try to finish up because the presentation itself was like 25 minutes, and now we're
sure. One of the things I want to say, because it keeps popping up here, is remind people that none of us on here have anything to gain from SRM other than what all humans stand to gain. We are not invested in it. We do not. We are not promoting it. If we wish we didn't have to use it. Think of it as chemotherapy. Okay. No one goes to the doctor and says, hey, I heard about chemotherapy. Can I just have some? No, you have it because you have no other option. And that's where we are. We are very quickly reaching the point of having no return. That's what this is all about, tipping points where we can't get back from. So we are not here as cheerleaders for SRM. We're here as cheerleaders for Earth and
Right.
people living on it, as we have for, many,
So,
many years. We would
so
like
the people who are going to
civilization to
make
continue.
money, first of all, I don't even know how you make money as a company on SRM. Maybe, obviously, some people think there is. We did interview the Make Sunset guys. They put up like a gram of sulfur in the stratosphere, and and they are making. I don't even think they're making money on it.
I don't even
overall,
know if they're
but
covering their
they do sell
costs.
credits. They sell cooling credits. Okay,
Yeah.
so you got that. But really, on a massive scale SRM, you're going to have the government do it. So the people who are going to make money are the airplane builders, because we're going to need about 200 specially built cargo planes that have more engines or more powerful engines to go, and bigger wings so they can fly higher. That's the major difference. So it's not a breakthrough technology, but it's something. And their current cargo planes aren't designed for that because there's no need to fly in the stratosphere. Some private jets can fly up that high, but they're small, so
Also
they're not.
depends on latitude.
Yeah, it also depends on that. So, but so airplane manufacturers will sell a few hundred planes. Not a big deal for them, I think. And then the other people are probably going to make money are the fossil fuel companies, because they sell the sulfur. They're the ones who have literally mountains. I'm not talking about like a figurative mountain. I'm talking about a mountain of sulfur piled up. When they process fossil fuels, they remove it. And now with shipping, they have to remove more. And so they're the ones going to be. So those are the people going to make money on SRM. And the people paying for it will be governments. And we're talking about billions a year, not trillions a year. So it's not even a big deal. It'd be like, you're promoting this because you get something out of it. It'd be like, oh, I'm invested in a chemotherapy company, so give me chemotherapy. I mean, it'd be pretty ridiculous, I think. Anyway, so let's keep going. Let's take one or two more, and let's move on.
So one of the twin questions I have here are about who is going to control SRM. You're going to have some sort of tuning. And the other, if we do SRM and the AMOC collapses, would SRM make Northwest Europe coaling worse? And I will start with an answer, and that is, the thing that is good about this is you can turn it off. If things are not going, if a huge volcano erupts, it's like you just don't put the next batch up.
Yeah,
but
correct.
You guys can give a better answer, I'm sure.
Well, that's true. And also, you would maybe not stop. You would put it in different places. You might emphasize more in the southern, over Antarctica next time, because remember, all this heat transport was happening going from the southern hemisphere to the northern hemisphere through the AMOC. If that shuts down, you could, I mean, again, you'd need a lot of studies on this, but you could keep doing SRM on the southern hemisphere to keep that cooler relative to the north. But again, you're dealing with a world that's in a world of hurt at that point. And back to the first part, we've done a number of shows on governance of SRM. It is a tricky subject. Actually, Leon just showed me a study recently that's saying the same thing that causes us not to act on climate, the same failure of governance that has allowed us to continue with fossil fuel emissions out the kazoo, as we used to say, is the same government management problem that's going to exist with SRM, right? So in other words, it's not a good sign that we can't get our shit together to fight climate change, emissions, let's say, of climate change. And how are we going to govern SRM, given that we can't even do the basics? So it's true. And I kind of think of it this way. Let's say a comet's coming towards Earth, and we can all get together and figure out how to stop it. But, that governance problem is very hard. People can say, you'll never get a really good governance. It won't be just. It won't be whatever. Well, you can say that, and then the comet's going to hit the Earth and destroy it. So, maybe you better get your shit together and figure out how to govern it at least well enough to get the job done. And it may not be the best, most perfect governance structure, but if you don't do it, by sort of not doing it is doing something, right? No action is action. No action means AMOC collapses and all these other tipping points across, and and billions of people die. So you've made a choice. It's just, and you made that choice just because the other choice was harder to do or something. I don't know. It just seems like a weak argument.
No action is gross negligence, and not just talking about SRM here, but right, that's what we see now. That indeed there's existential risks, literally, for the coral reefs. For like you showed the tipping points. There's existential risks, and not doing something because it's incomfort, like doesn't feel comfortable, or there's some difficult subjects you have to think about and talk about and find agreement to. That's gross negligence, and I think even criminal gross negligence in many ways, because of course the impacts are worse than many. Like, it's very hard to comprehend how bad it really is, and yeah, so you're right.
Okay. I see some comments like, "Hey, here's an example. Hey, bud, didn't science and technology get us into this predicament?" So, okay, it's a nice little meme. And yes, the science, fossil fuel technology is what got us into this mess, by the way. And so it's kind of implying, therefore, you can't use technology to get us out of this mess. And maybe that's true, but that just means then we're screwed, right? So, smoking was a technology. Tobacco was a technology we developed long time ago, and gave people cancer. Then we used other technology to kind of help relieve the cancer. And it would be like saying, "Hey, you shouldn't have cancer treatment because that's technology." I mean, I don't know. It just seems like it's a red herring kind of argument or something.
In a way, but it's also, I understand the question, and it's hard to see the inadvertent, or the inadvertent by effects, or the result of doing scientific research or developing technology. It's almost impossible to know, right? Whether it's the development of GPS system, I don't think the ones who started working on that would know that the main use wouldn't be bringing nuclear weapons to their target, but to bring people to their coffee places, or to the things, beneficial things like the development of the washing machine and similar household technologies, helping women to become liberated, and to also enter the workforce, and all these other impacts, beneficial, some less beneficial, that stem from technologies are almost impossible to predict. But what we can predict, we need to try to understand better, right? Indeed, like you're not going to give people chemo without doing the scientific research. You need to do the research and then decide whether you're going to give the chemo, right? Because if the medicine kills the patient, but it takes care of the chemo, the cancer, the patient is still dead, and you don't want that, right? And we don't want that with SRM either. We don't want to kill the patient by developing by giving a medicine which hasn't been studied in.
Although I think that even when we know, first of all, as you pointed out, all technologies that have positive benefits also have negative. I mean, just look at the internet and social media. That gave us Trump, right? So it probably wouldn't have happened when Walter Cronkite was on the air when I was a kid, filtering the news. So you got sort of real news rather than the crazy stuff. But let's take a look at AI. AI clearly has potentially devastating impacts, including the extinction of humans. And the people developing it say, "Oh yeah, there's a 20% chance." These are people developing of wiping out humans. Yeah, that's true. But we got to do it anyway, because if I don't do it, the next guy's going to do it. So I'd like to do it. And it's just, that one is, we know it's, I mean, everyone can say, oh, I'm going to lose my job over AI like next year. I mean, it's not like even a 10, 20-year out kind of thing for many people. Look at self-driving. That's AI. And all the drivers are going to lose their jobs in 10 years or something like that as that kicks in. So we know it's going to happen.
Don't go with me on that, because that we need to lose the drivers. Human driving is the problem.
Well,
we slay
you could say
1.3
that's a
million
positive
humans
thing.
every year and don't bat an eye.
No, there's way fewer deaths, way fewer cars, by the way, because there's a lot of positive benefits. Don't get me wrong, but we also know that there's negative things, and it doesn't matter. We can't stop ourselves, I guess is what I'm saying. Hey, let's let Eli in for one last comment or question, and then I think we'll finish up. Hey, Eli, welcome. Get back. Yep, you there? Don't hear you. You are on. All right. I don't think he was dropping out all the time, so I don't think that's working. So, Stacy or Leon, you have any final thoughts before we call it quits at 11:30?
Mine isn't SRM related. It's just to thank people for being here and for watching, especially our international friends and especially and our doomer friends. It's so funny. I have trouble like participating in life in certain things because I'm so concerned about, our activities that are causing the demise of the planet. And so I don't know how to adjust. And this is the first time where I feel like, oh, this might not be the most important topic in the nation at this time. And it's so unsettling. So
Yeah. There's a lot of crap going on.
Yeah.
In the world, and it deserves a lot of attention. However, one thing it is doing is it's taken. There was never enough attention on climate change, but whatever there was, it's now a third of what it was, or something like that, because of all the craziness politically that's happening. And climate change doesn't care whether you pay attention or not. It's going to do what it's doing because of physics. And so that's one reason we're trying to keep up the discussion here. Yeah. So anyway. So I want to thank everybody, along with Stacy, for that. To thank everyone for joining us. Please like and subscribe to help spread the news of this program, and that people can learn about climate change here. And thanks for everyone doing what they're doing. And we will see you next time. Bye-bye, everyone. Take care.
Thank you. Bye.
Bye.